have influence, and we're going to quantify the damping and using because we expect the vibration is going to decay, be suppressed due to damping. So last time we have introduced the concept is delta log rhythmic decrement. Okay, and that one is delta equal to log what's that formula? Hopefully that is that one. Yeah. Okay. So last week we introduced that one, and basically this is saying, by definition, is that right? There's a no log here. Basically, this thing is the log of the amplitude A1, A2, and what is A1, A2. So here, if we can describe our vibration of the damped systems and in graph, and if we draw the graph like this, okay, the maximum, this is the first one, the amplitude is A1, the second one is A2. So A1 over A2 is something like this. Or equivalently, if you're going to say A2 over A3, or that is also equal to A2 over A3. Basically, that is the ratio of the amplitude, the one period apart. Okay, so that's the meaning of this one. So today, we based upon this, the understanding, we have introduced another term called the loss coefficients, and that is the way we can describe by this. Earlier, I have shown you is we know the damping ratio, the energy is the rate of the energy change is negative. Okay, so that means I think this one total energy. Let me rewrite this one again. Then for the total energy is E. Okay, that is the kinetic energy plus potential energy. Okay, and kinetic energy we can describe for single degree freedom system is mx dot square. Potential energy is kx square. Okay, so basically this one is for such a system. Okay, K, and this is M, and degree freedom here. Okay, and total energy doesn't matter that system is damping, has a damping or not, and that total energy simply is kinetic plus potential energy. And last time we have done is we try to calculate the derivative of the total energy, and we calculated. And here, let me do this quickly. Basically, that one we found is equal to mx double dot plus kx and times x dot. Okay, and a few steps in between, and I skip it, but that is the way. Okay, right now for undamped system, we know this term equal to 0. For undamped systems, mx double dot plus kx equal to 0. This is for undamped vibrations. However, for damped vibration, if we consider damping ratio here, then the equation of motion for damped systems okay, like this. So from here you can see basically this term in the bracket equal to minus c squared. So that one equal to minus c squared. Minus c x dot and multiply with this term. So basically that one equal to this. So this is negative. So for damped system, we know the total energy is dissipating over time. and something like this. Either you want to draw it in terms of the time, the displacement versus of time, then you can see the magnitude of the damping basically is decreasing. And decreasing is in a regular pattern and follow up by this rule. Or otherwise, if you want to draw the response in, we call the phase diagram. And again, we know the phase diagram, basically you draw it in the two-dimensional plot in terms of the displacement, velocity, or scale displacement versus scale velocity, whatever. So that's a phase diagram, and in this case, that from the initial conditions, we know that eventually going to convert into zero. So eventually, for damped vibrations, it will stop here at right origin. That means zero displacement and zero velocity. Okay. So that is in concept. We know the energy is going to dissipate, and the loss coefficient basically is tell us how quickly the energy is going to lose. And that one, basically this coefficient, let me define here. Basically, for compared to this decrement, this definition delta is regarding the ratio of the displacement, and this one is tell us the ratio of the energy, the one period apart. So by definition, let me do this. This one is by definition is delta. Okay, so here the U representing is the potential energy, and delta U is the change of U in one period. Okay, so we can do the calculations here, and the delta U. For example, if we consider okay, so for example, the U here we pick up, for example, is in here I drawing is the first and second, and for notation, let me say this one corresponding is the AI about that. Okay, I can be, for example, for this graphic expression is I equal to 2, simply AQ. But in general, let me using the index AI to indicate that is the ice, the amplitude of the cycles. Okay. So for this case, we can see the potential energy corresponding to this one. That will be 1/2 K times AI squared. Okay, and then the next one, after the one period apart, this one, the magnitude equal to AI plus 1. So we can calculate I plus 1, the potential energy corresponding to one cycle later, and that is 1/2 times AI plus 1 squared, right? Okay, so we can proceed to calculate delta U. Simply is delta U I minus U I plus 1. So that one is 1/2 K, and AI squared minus AI plus 1 squared. And we can play around. So basically, this one is equal to K, and we factorize this term, AI plus AI minus A plus 1 times AI plus AI plus 1. Okay. So now we proceed, and so this is a change in the potential energy in one cycle. if we compare this change respect to the potential energy and the corresponding to here, so that delta U divided by delta Ui, then from here we can proceed and we can do the calculation. Simply is divide those terms by this. So simply that will becomes AI minus AI plus 1, AI plus AI plus 1, and AI squared, right? And K over 2, simply that is a common coefficient. You simply cancel from the numerator and denominators. Okay. So furthermore, and we can do this. So from here, for the numerator is a multiplication of the two terms. For each term, we divide by AI, because here we have two AIs multiplied at the denominator. So that means I distribute the divisions into individual terms. So basically that becomes 1 minus AI plus 1 divided by AI, 1 plus AI plus 1 divided by AI, right? And then from here we can relate to our things here. So using the logarithmic calculations, the definition basically this one is 1 minus. And again, the ratio between the amplitudes 1 period apart basically is the exponent of delta. So from here, let me rewrite here. So delta basically by definition is log of AI plus 1. So therefore from here we know the AI plus 1 equal to exponent of delta. Okay. So right now in our derivation we need is the inverse. So that basically AI plus 1 divided by AI equal to e to the minus delta. So we pick up this information into here. So that is minus delta. And 1 plus e minus delta. Okay, so we implement this one. Basically this is 1 minus e minus 2 delta. Okay. So from here we have the information we can put into here. So basically that is 1 over 2 pi . Minus e minus 2 delta. Okay. So that is the calculation. So with this formula in mind, then basically we can directly utilize the result. And again here sometimes that is come to the little bit the standard. Sometimes people didn't scale by 2 pi, and sometimes yes. And here in our textbook, since we adopt this one, so I follow up divide by 2 pi using, so simply consistent with our textbook. Okay. And the other side note is not that critical, but here let me mention, when delta is small, then basically the whole terms can be approximated simply by okay. So likely you can expand it using Taylor series expansions, and you can expand it at using Taylor. That's approximate equal to at 1. Okay, that is 1 minus 2 delta times something like this one. Okay, so something like this one, these are higher order terms. So simply when delta is very small plus higher order terms, these are exact. Okay, the higher order terms basically that is a function of the data square, data cube, etc. So when data is very small, basically the influence of a higher order term can be very small. So that means if you plug in this expansion to there, and that is the good one. And how good approximate for how small, corresponding to how small the delta is, I would say this one only won't take too much time in punching calculator. I would suggest why not we just use an original one. Okay. So that is for this page. And any questions? Then we can look at one example.